Okay, let's have a look at how we derive and use what's called the ideal gas law. We've already seen that we can measure four things with gases. We can measure pressure, temperature, volume, and the mass or the number of particles of that gas. So we set up four different relationships. We've got what's known as Boyle's law, which is the relationship between pressure and volume. And what we found was that pressure was inversely proportional to volume, or pressure is proportional to 1 over V. Now we can also rearrange that as volume is proportional to 1 over P, or inversely proportional to pressure. In Charles' law, we found that there was a relationship between volume and temperature, and we had to have that temperature in Kelvin. So we found that volume was directly proportional to temperature. We also had a look at Gay-Lussac's law, or Amonton's law, and we found that pressure was proportional to temperature. Pressure being proportional to temperature. And once again, we need that in Kelvin. And finally, we had a look at Avogadro's law, which was the relationship between volume and number of moles, or the amount of gas particles that we have there. And we found that the volume of gas was directly proportional to the number of molecules that we have, and we measured that in moles. So from these four relationships, we can actually derive one single equation that equates, or that uses all four of these terms. So we're going to use Boyle's law, Charles' law, and Avogadro's law to derive this single equation. So we have our three proportionalities, and they all relate back to volume. So if we derive our proportionality for all four terms, we find that volume is proportional to temperature from this one, from Charles' law. Volume is proportional to number of moles from Avogadro's law, and volume is inversely proportional, or proportional to 1 over P from Boyle's law. And that gives us our proportionality of volume is proportional to T times N over P for this set of, or for these measurements. So from this, we can actually see that pressure times volume, so we transfer our pressure to this side, is equal to some constant, so we take out the proportionality, times the number of moles times the temperature in Kelvin. And for our ideal gas, we substitute our constant K for R, and we call this what's called our gas constant. So our derived equation for an ideal gas is pressure times volume is equal to the number of moles times our gas law constant times our temperature in Kelvin. So the next thing we have to do is work out what our value for R is. So to derive our R value, we've got to take into account standard temperature and pressure. So we have 1 atmosphere, and our volume is 22.41396 litres, and our temperature at STP is 273.15 Kelvin. And we also have 1 mole of gas present as well. So we've got our equation PV equals nRT. We rearrange for R, so we divide by N and we divide by T on both sides. So we get PV over NT is equal to our constant R. Now, if we use this set of values, so our pressure is measured in atmospheres, we can work through this calculation and we come up with a value of 0.082057, and our units for this constant are litre atmospheres per Kelvin per mole. So that's one constant, one commonly used constant for R. Now what happens if we substitute in pascals for P? Well, we go through exactly the same process, so we isolate R. This time we put in our value of 101.325 pascals for our pressure. We also have our volume as metres cubed, because we're now changing our units. Temperature stays the same, and number of moles stays the same as well. If we go through this calculation this time, we get a value of 8.3144 pascals times our meters cubed all over Kelvin times moles. So why do we get the two different values? Well, we've used our different pressure units, so of course we get a different value. Now, it's important to note at this stage that this value here, we don't commonly use Pascal meter cubed. Instead, we use kilopascal litres for this particular value. So when we look at this constant, we actually see the units for the constant are kilopascal litres per Kelvin per mole.